All right, hello everyone, and welcome to South Carolina Linux Users Group in Greenville here, upstate Carolina Linux Users Group, and in Columbia Linux Users Group. Hey Ben.
Hey y'all.
Tonight we've got Duncan. Is it Michael or?
Yes, Michael.
Duncan Michel
Yep.
is going to be giving us a talk on regular expressions in focus on cybersecurity.
Yeah.
And I think I'll just let you take it away then.
Cool.
Thanks for everyone for coming tonight.
All right, everyone. Like I said, my name's Duncan Michel. I named this. It's kind of a joke on a classic cyber paper. But basically want to talk about regular expressions, how they're useful as a tool, and for a small part of it, some of the security implications of them. So this is me. I had a bachelor's in computer science a while ago and worked for a while in the Army. And the last 3 years of that time, I was able to be part of the cyber mission, which is where I got to dive back in a little bit of depth to some of the stuff that I love. And then for the 5 years since I've been out, I've done a variety of some security research, content creation for training, and detection engineering, which is a big part of my job right now. Hopefully getting OSCP here in the future. And at one point I had some other certs and I let them expire because I didn't really care that much about them. Next up, this is what we're talking about, regular expressions. Just kind of a basic 5 Ws. And then I wanted to go over some like how to use the basic syntax. I'll mention what some of the advanced usages are, but we're not going to dive into those tonight. And then a couple demos. So just as a quick test in the room, see what pace to go at. How much of you would say like I use this on a daily basis, or I feel extremely comfortable with regular expressions? Cool. And who's like, I don't really know, haven't touched it at all, basically. Cool. Absolutely fine. Just trying to get an idea. So that's what our agenda is going to look like. Next thing, this is what regular expressions are, just kind of a basic definition. I've got like the Linux Foundation and then also Microsoft.net, but I actually really like one of the things that it says in here. So it's essentially, it's a sequence of characters using like a specific syntax, which we'll go over, that is meant to find patterns. The pattern, the regular expression itself is like an interpretation of a pattern, and that interpretation involves character literals. So like I want to find this character, operators, which help describe like logically how much of it you want or whether you want this or that kind of thing, and constructs, which is just like a little more complicated logical flow. This is the basic why. At the end of the day, regular expressions are all about pattern matching. First of all, you want to find a match, and then a slight extrapolation of that. It could be you're trying to find it in order to extract that data, either from like a distributed data set, or like you want to pull all of something out of a file, or you want to like scrape a web page and find all the links, for example. Those are some of the situations which you might use regular expressions to extract data. Another way you might want to do pattern matching is you want to find that string and then replace it with something else. So this basic search and replace is a classic usage of regular expressions. And then another one might be to validate input, especially if you're using it. This is a lot of times one of the ways it can be improperly used, is when you use a regular expression in like a web application, for example, to validate some piece of user data. And if you don't do that properly, and your regular expression fails, that's where we get a lot of classic vulnerabilities, or even denial of service, which we'll talk about later. This is, to be honest, slightly generated by AI, but it's a short history of regular expressions. At the bottom line is back in the 50s is when some of these like, old school computer scientists wanted to find a way to represent natural language using symbols. And that kind of progressed in the fields of mathematics, and then finally in computer science, as in one of the original Nix distributions, introduced using regular expressions for pattern matching in QED, the text editor, and grep, which exists today. And as computing systems have become more uniform in our world, like it's become incorporated in everything, basically, programming languages, different web applications, and so on and so forth, and the power available using some of this more advanced syntax has become more complicated. What basically, there are some constants, and we'll talk about what I would consider the constants in regular expressions. But at the end of the day, there are a lot of different types, flavors, like slight variations on the syntax. So like I said, we'll hit like the major points tonight. But if you choose to like use this in the specific system or language that that you tend to do on a daily basis, then at the end of the day, like look up the manual. That would be my suggestion. Like see what the slight variations of that are going to be. But PCRE, Perl compatible regular expressions, which is the most popular form of representing them, is kind of what we're going to be talking about tonight. So this is a syntax overview. The basic syntax involves literals, wildcards, anchors, classes, groups, alternation, quantifiers, and escapes. And we're going to go over what that looks like. But what most people see this as, if they're unfamiliar with it, is kind of what this comic represents, which is just random typing on your keyboard. So literals is basically like what I type, I find that. So classic would be like you're typing literal letters and you want to find exactly that. So I've got an example here. If your regular expression is ABC, then it'll match these strings up here, because you might notice like even if there's data before or after, like where it finds it, like that is still considered a match. There are other things that we can do to restrict where we find it and what is around it, but at the end of the day, that's what a match is. And this does not match ABD because it didn't find C. So that is the character literals. In fact, like if you're typing something in your search bar, congrats, you're already doing it pretty much every day. You're searching for a literal expression. The next thing would be wildcards. And in PCRE, this is like the dot. So it's basically saying find literally any character in that space. So ABC dot would match all of these that I have here at the top. And it doesn't match ABDD because it does need to find a C. It doesn't matter like that there's a wildcard at the end. It still has to find everything else in the expression. So wildcard matches anything. Also, you might notice that I've got some graphics to the right. I'll show what tool uses that a little later in the presentation. But if you're like new to it and you just like your mind works graphically, that can be a really helpful way to like see what is this regular expression doing. Next would be anchors. So anchors is part of what I was saying, that restriction. Where exactly do I find things? So the caret and the $sign are your two anchors. Caret says this has to be at the beginning of the input. There are some ways you can, we'll talk about it later. Basically, you can say like, this is the beginning of all input, or this is just the beginning of a line. At the end of the day, what's worth remembering is an anchor says like at the beginning of input, this is where my expression starts. So for example, in the caret ABC, that means that it has to be at like the beginning of this sentence, for example. So it will match here. But this second input that I have that starts with a Z and then ABC, it will not match because there's a Z before the beginning of my expression. So at the end of the day, it says like the expression has to start here.
What's the $sign?
$sign means that the expression has to end after this. Sorry, the input has to end after this expression. So ABC dollar means like, at the end of the line, this is where the expression happens. If there's anything following it, then it fails. And it's not a match. So anchors help restrict where we find things. Next up is classes. This is where you want to specify, like, I want it to match anything in this collection. So if I have a class, well, in my example, I said A, like C, D, and E are all inside of that class. So it'll match A, B, and then C. Now, technically, like it doesn't match the D following because the expression ends there. There's a way that we'll mention in a second, quantify how many characters we have. But at the end of the day, it will match a single character as long as it's inside of that class. So our examples are ABC, ABD, ABE, because all three of those are in our class. Some of the don't matches, like we find AB, but then something else is there. Or yeah, it's like AC, like it matches something in our class, but we never found the B. So essentially you still have to abide by the rest of the expression, but for that position, it can be anything inside of the class. There are some special like shorthand for classes. So /D matches all numbers, and it's D because it's digits. So 0 through 9, you can represent with a /D instead of typing out this class every single time. Also, I think I forgot to mention, but you can see it represented there. You can literally name everything in the class, or if it's part of like a larger character set, like the alphabet or the numbers, you can use a shorthand of like 0 to 9. So you can use a dash to be like, I want anything 0 to 9, or I want everything A to Z. So that's a sort of shorthand you can use to like not have to type out literally every character of the alphabet inside of your class. Surprisingly, there's not exactly a shorthand, at least in PCRE, for just the letters. But you can use W to match all word characters. And this is because it's like commonly seen in like variable names, email addresses. So like domain names, like most of those fit inside of the word class. And then /S matches all white space. So your tabs, new lines, like literal space, and carriage return, all of those match the /S, which is white space. And then the capitals are literally the inverse. So /D is everything except a digit. /W, everything except one of these word type characters. Also notable in the word type characters, in case you don't see it, is the underscore. For some reason, underscore is in it and hyphen is not. I don't know why. I didn't make it up, but that's how it works. So these are classes. And then the next syntax that we're going to talk about is groups. So groups would match the entirety of a sub pattern within the parentheses. So this is where you start adding some complexity and some like larger logic to your expressions. Is I want to find AB for sure, but sometimes I want to find CD and sometimes I don't. But as long as like I find AB and then CD or not CD, then I'm good. So it matches here and it matches there. Sorry, that's the question mark is part of quantifiers. It was hard to talk about one before the other, so I talked about groups first. The question mark says like it's there or it's not. So sorry about that confusion. But essentially, yeah, groups allow you to say like everything within these parentheses matches, or the expression fails. Next up is alternation. So alternation is basically or. So you often see these, again, inside of groups, but it's basically saying it creates a branch. So you can call one subpattern or the other. So I have A, B, C, or D, and then E. I actually didn't do the best job of demonstrating this because you could kind of do the same thing with a class, and that might not tell you why this is different. So if you could imagine that it's A, B, and then inside the parentheses CD or EF. So it basically says like I can find this or I can find this, and then I continue on with the rest of my expression. So it basically is a way to create branches, because sometimes like you want to allow for like a lot of complexity, and that's where alternation comes into. Next up is quantifiers, and we've got a lot of these. So the asterisk, plus sign, question mark, and the curly braces are all basically saying how much of a particular character or particular class or particular group you want to find at that position in the expression. So starting with the asterisk, this is 0 or more of that particular character. So ABC asterisk means I could find 0, but I could also find 10. I could also find 20. So I've got a couple examples of what matches look like and what failures to match might look like. So this bottom one here, AC is self-explanatory because there's no B. The reason why B doesn't match is because there needs to be an A. But if it was just AB, as we can see under our matches, then that would be fine because we found 0 C's and this expression would match. The plus sign is 1 or more. I want to find at least 1, and if I find more than that, then that's okay too. So it actually looks very similar to our ABC example, except I do have to find at least 1 C for this expression to be valid. The question mark, we actually already showed. I think I used this exact same example. So it's basically like I can find it or I cannot, and both of those are matches. And then finally, the braces are a discrete quantity. Like I want to find exactly 2 B's in this particular expression that I'm demonstrating. And then you can also specify a range. So for C's here, like I want to find anywhere from 3 to 5. So 3 is fine, 4 is fine, 5 is fine, 6 is not. And you can see examples of that in my matches and does not match strings up here. And finally escapes. So as you can see, like we use a lot of special characters to build these expressions. So what happens if you want to find a question mark? That's where the escape comes in handy. And you can basically say like, I literally want to find this special character in the expression. So this is how you literally represent the special characters, which you can see in the matches. And then I think I have, yes, on this slide is an example of like all of the special characters that are used in these regular expressions. So if you want to literally find one of these, then you do need to escape it with a backslash. With one exception, and I put it up here, hyphen, normally you do not need to escape it. But if you put a hyphen inside of the class, remember we use like a hyphen to say like 0 to 9, like you can use it to represent a range. So if you literally want to put a hyphen inside of a class, then you should escape it. Other than that, everything else up there always needs to be escaped. And I think, yes, that is the basic syntax. So before I move on, that was like a fire hose of information, especially if you've never seen this before. So do we have any questions about some of the basic syntax before we move on? Cool. All right. So we're not going to talk about this tonight, but just to explain, there are a couple more advanced things that you can do with regular expressions. One of these I will show a couple different times, which is mode modifiers or flags. This is basically a way you can say like, I want this expression to be like case insensitive, which means, you know, it doesn't matter what capitalize or lowercase. Another modifier might be like, I only want to match on like a line of text as opposed to like the entire breadth of a piece of data. The groups, you remember those were in parentheses. Those can actually have names, which is really useful if you're doing like a search and replace, or if you are capturing that data and like porting it into, you know, a different system or something like that. So named groups come in handy when you're doing something with a subset of what you find. Back references are, so you may not have noticed, I forgot to mention it, but I'll scroll up to the groups. So there's 2 different types. The regular parentheses are what's called a capturing group. So it like the regular expression engine will just record, I found this group. And that allows you to do something with that. So, you know, you could say like, I want to find Duncan and then, you know, some character, and then I want to find Duncan again. But I don't know that it's going to be Duncan because it might be Jace. And I want to find Jace and then a colon and then Jace again. And like that particular pattern you can find because you say like, I want to find parentheses, literally any word, colon, and then that same word. So that's where capturing groups allow you to reference things that you found, but you don't know exactly what it's going to look like before you match on it. And then the question mark colon, that's a non-capturing group. That's basically saying, I want to group this stuff together, but I don't care what happens to it after I find it. I just want to make sure it's grouped together. Back references, look aheads, look behinds, look arounds. I'm not really going to go into it, but it basically gives you a little bit more flexibility for where you find things. And conditionals and then replacement. It's got some more advanced things you can do with groups. I'll just leave it at that. So that's some of the advanced syntax. So if you are interested in exploring regular expressions further, I'm really comfortable with the basics and I want to do some really cool things with it. I suggest exploring some of those, and I'll give you some references in the end. This is an example, by the way. You don't have to memorize this. In fact, like until you do it on a daily basis, you won't. However, if you like pull up Regex 101, which is a tool that we'll be using, or I'll be using in the demo, then it's got this very handy quick reference. So literally pull that up and it tells you all of the things in terms of syntax that you might need to use as you're building one of these. Common pitfalls. One would be just kind of overcomplicating things. It's hard to like nail down exactly what this looks like, but you're trying to account for too many different like branches, and like all of a sudden your regex like grows to be like 100 characters long, and you can like barely even read it. That tends to be a common pitfall in like developing something that's robust, because if you can't read it and understand it, you can't really maintain it, and a lot of these do need to be maintained. Another common pitfall is not testing. I recommend, like, as you're building one of these, you make a set of like, I want to match on this, I want to find it, but I also do not want to match on this input. And so having both of those makes it useful for making sure that like there's something that you didn't overlook. And then not understanding the nuances. One of these, like the classes that I mentioned, like the fact that like underscore is in the word class, but hyphen's not, like that's a nuance. So if you're like expecting something to be there and you're just kind of like using that class just like willy-nilly, then you might overlook a particular case. Another one, so the greedy regular expressions by default, there's actually one flavor, I can't remember which one, that is like not greedy by default, but most of them are like, if you say like, I want to find one or more C's, like, that C plus part of it, like it's going to go to the end. Like it's going to, find as many as possible and say like, this is the match, as opposed to like finding like the first iteration of that. So basically like try to understand the nuances of what you're working with and make sure you do a lot of testing. Is what I would boil those down to. And then speaking of pitfalls, is the idea of efficiency. If you were looking at these, which would you say is the more efficient expression? If you work with these regularly, if you don't.
Assuming they do the same thing, B is obviously easier to read.
They don't do the same thing. But they do some similar things, like they find about 2 or 3 characters, maybe 4 characters of data, and there's a little bit of branching involved.
B has less capturing groups.
It does.
A starts with a constant. That seems like it's easier.
That actually that ends up being the deal breaker. So we'll talk about it in a second when we talk about regular expressions and analysis service. But regular expressions under the hood build an engine that it's called a finite automaton. And my like 10-year-old computer science history or education is failing me the nuances of that. But at the end of the day, it's like got a discrete system for how it goes and finds all the things. And having a single starting point is going to be a lot more efficient than having 4 potential starting points. And I've got a piece of data that explains A is more efficient, and I'll show you all how that works.
And to tee off of that, when Duncan covered the anchors of startup line, end of line, those are probably the best performance things you can do if you can consistently use them, because the hard setting, here's where my regex is beginning, or here's where my regex will end, and it's smart enough to know to match based off of that. So that A was exactly like A.
Right. So what I like to use when I'm like testing the performance of a regex is, as I throw it in, like, this is regex 101. So yes, I can. Excuse me. There we go. How's that? Good. Can everyone see that? Let me do a little further. Okay.
This is regex101.com.
Yes, regex101.com. And it's literally just, I like to think of it as a test bed. So you just put your regular expression up here. You can throw some flags on it. I'll just not say it. It doesn't really matter. Anyways, and then what it's going to do is it's going to start here and examine every single character until it finds a match or fails to. And it's going to find the match here at the end. So if I put a valid match at the beginning of these strings, then they're going to look pretty similar. But as the size of the data that this regular expression is parsing through increases, then the efficiency matters a lot more. So I'm looking up here, and there were like about 1,200 steps that this regex took in order to finally find a match. Whereas the other expression, and the reason why under the hood is if you think about like the engine that this is producing, like it's looking at A or B or C or D before looking for an E. So it's going to look here, and then it's going to look here, and then C's, and then D's, and then it's going to like skip a bunch of this stuff because it doesn't find anything, and then finally like look again down here. Whereas this other expression only goes through 200 steps because it looks at all these A's, tries to find a match following them, fails to, and then skips all the way down here and finally finds a match. So yeah, basically, if you can eliminate the number of branches within reason that your expression starts with, then you can produce a more efficient one. So, and we'll go back to that in a minute. Nope, this one. So that is what, and efficiency kind of comes around again as we talk about regex denial of service. So this is an attack on the availability of a particular system. Often we're talking about like a backend for a web server, something that's like parsing user input, and it causes downtime in that vulnerable service because that poorly formed, that inefficient regex basically consumes too many system resources trying to parse a very large malformed piece of data. Oh, and that's actually the phrase that I was trying to find: non-deterministic finite automaton. That is, again, under the hood. If you're like really nerdy computer science guy, that's what it is creating in order to parse through all of the data. And then the intended behavior, like that a regex does fail, so that it doesn't like continue potentially consuming system resources, that is exploited is something called catastrophic backtracking. And the way these work, this is a couple examples that I pulled from a paper, educational paper, probably one of the ones that you found while you were looking at this particular problem set online, in which like a lot of these have been examined educationally, and there are some like bug bounties and everything that have tried to find these in the wild and identify them. But essentially, some of the things that you're going to see is kind of like an unclearness in like which part of the data is being parsed. So in this particular one, I'm looking at the function one. It's a source code. It's like function and then a wildcard character. I can have 0 or more wildcard characters, and also it can be there or it's not. And then you find a parentheses, and then again, 0 or more wildcard characters, and then close the parentheses. And it's basically like a lot of wildcarding and wildcarding or the plus sign nested inside each other, like this particular one right here, like a white space, 0 or more white spaces inside of a group that is like one or more of these groups. And you can see like there's a new line and then a white space class right next to each other, and like a new line's in the white space class. So basically, like where there's a lot of ambiguity as to like which character is being matched, it creates way too many potential branches for that that underlying regex logic to basically like narrow down and be efficient. So an example of this, well, here's a real world example of it. Stack Overflow had this particular regex that was put into their code back in 2016. And because basically someone uploaded a very large, I think, piece of white space into their system, it brought it down for 34 minutes. So I'm gonna again skip over to Regex 101 and kind of like let you see what this looks like practically. So this is what a reasonable regex would look like if you're trying to find a bunch of A's. And And it basically takes 2 steps. It like finds one, and then it finds all the others, like almost instantly. However, the secondary regex, which you can see, it's like finding an A or more than one A, and then at least one of those. Like this is about 7,000 A's that I put in here. It takes 15,000 steps to match on the exact same input. So if you can imagine this particular regex existing in some particular server and someone realizes that's there and they upload, I don't know, maybe something like 50,000 A's, and then all of a sudden we have catastrophic backtracking and the system just fails. So this is basically a way in which, if you know it exists, you can create a denial of service on a real world system.
So did that scale like exponentially? Or
Yeah, it scales exponentially because like if you imagine like it's each one of those like creates a branch, like every single position creates a branch. So you're at like 1, or 2 to the, I think it's like 52,000 squared at the end of the day. So here's some tools. Regex 101, we just played with that one. A couple others like Regexer. I like this one because it creates just creates a lot of like visual feedback for the regex you're creating. Regexper was the tool that I was using to create those visualizations that you saw earlier in the slides. And then DebugX is it's similar. It also creates like a visualization, and you can use it for debugging, just like Regex 101, but like the GUIs, like it's just a little smaller. So like I like Regex 101 because I can throw like as much input in as I want, and I just kind of like see it all pretty easily. That's my tool of choice for having been a little more experienced with this. But like if you're if visual helps you a lot and you don't have like a giant amount of input, then DebugX can be kind of helpful as well. So practice. How about matching an IP address? How would you go about solving this problem, using some of the syntax that we've talked about so far tonight? Anyone want to take a hack at it?
The lazy way.
Sure.
/b plus /dot /b plus /dot /b plus. Repeat.
Nice. Yes.
But that's a little bit too
Similar to this, which is what a lot of people would probably say.
That's the lazy way to do it.
Yeah. Let me pull in. And remember, we talked about match and don't match. So yes.
what is the B?
Okay, so \B is a boundary. It actually does not consume a position, but it basically says there is something that is not a word right here. And that something may be the beginning of input. So like the anchor is also acceptable to be right here.
But it's not a white space.
But it can be a white space, yes. But it's not a word. So it's not A through Z, lowercase or capital. It's not a number, and it's not an underscore. So yes, /B is helpful if you want to like try and create a word boundary. It's reliable at doing exactly that. And it does not consume a character. So like if I put, let's see, a space at the end of this, it doesn't actually match on the space itself. It just says like, yep, there's a space there. So that's the end of input. We're good. So yes, this I specifically said between 1 and 3. Like Eric was saying, the lazy way would match on all of these valid IP addresses. Unfortunately, it also matches on these invalid IP addresses right here. If you can see some of this input. So any thoughts on how we might tailor this to be a little more accurate?
The range restricts each digit to what it could actually be.
Yeah, that's basically what you end up doing. And yes, and we'll do it just for the first range. And then I'll show you what the final one looks like. So we know that it can be anywhere. It can be a single digit or it can be 3 digits. So it could be a, and then it gets a little more complicated. You can't just say like, oh, it can be 2 or 1, and then any digit, because unfortunately that also matches 256, which is invalid. So then you have to separate it out, and so then you're creating like a group. So you're like saying like it could be 2, and then let me get rid of that real quick. This is alternation, the 1. And then, yes, or any 2 digits, or any digit, which actually you could basically do that. And then for 2, you could have anything like 0 to 5. Actually, you can have anything 0 to 4. And then any digit. Or you could have 5 and anything 0 to 5. Let me mentally think if that's right. Yes, I think that's valid. And actually, this doesn't work for the very first position because you don't want to match on a leading 0. But basically, this is what most of the rest of them are going to look like. So you have to like think through all of the use cases and develop like a couple different branches. The final regex looks like this. There we go. As you can see, it doesn't match on any of these that we don't want it to match on, and then it does match all of these valid IP addresses. So, so yes, that's what ours looks like. So swapping back over to our slides real quick. Yeah, we talked about this. This is kind of like usually a first hack at it. Then we got to think about our test cases, and then we arrive at something like this. If anyone's curious how well ChatGPT does with this particular problem, they also arrive at the lazy way for a first attempt. Also, we're not even going to talk about IPv6, which it does also attempt at. And then once you get some feedback, it does finally get to like a decent solution, which is not bad, considering it basically has all of Stack Overflow to work with. So, all right. So think about like, how do we apply this? And again, I'm coming from a cyber background, so I'm thinking specifically cybersecurity context. And just because I tried to narrow it a little bit, I was talking blue team, but there's also some red team applications, especially like for developing word lists, or for, again, like trying to exploit regular expression DOS, so on and so forth. But specifically within the blue team, some of the ways that we could use this: searching through logs, creating alerts, and malware analysis. This is a lot of how I use it, and also creating YARA rules, another way that I tend to use it. Code review. So if you find yourself doing a lot of code review and you see like a problematic pattern, you can develop like a regex in order to search through code bases instead of having to manually comb them, which sometimes you still will probably have to manually comb them, but at least that makes your job a tiny bit easier. If you want to get really wild, you can do regexes searching for regexes, which is also fun. You can do some flexible SIM search strings, which is hopefully a demo that I'm going to add into this eventually, but it's not in this particular iteration. And then putting it into your scripts. So basically like putting these inside of the code that allow you to do some more complicated things. And then, yes, this is XKCD. Basically how you feel once you learn these for the first time, and you try to use it for a while. All right. So going from here into demos. So first of all, if you use grep, you're already doing it. So that comes in kind of handy. Close this down real quick. So kind of naively, whenever you tend to try and like find something, especially using grep in a particular log, like yeah. Oh, sorry. Yes. Yeah. So font. There we go. Hold on. No. Hold on. Let me go preferences. Under view. Yeah. No, it wasn't. I think it's probably because I'm in a VM. And it's there we go. How's that? Better? So if you're gonna grep the for like I pulled down a web log from a HTTP log from the National Cyber, it's basically a cyber defense competition from back in 2012 because that was the data available to me. And say like this was your web log or your web server's data, and you wanted to see like is someone trying to like throw SQL injection at my particular server. So you could search for something that to be common in that kind of thing. And then I'm going to pipe this to word count for the number of lines this is going to return. And you might find yourself having to parse through like 2,000 different lines of that particular log. This is the, I think, Bro data set, the HTTP log from that, which I like a little less than access.log because it interprets all of the URL encoded characters. But so you might find yourself like wanting to narrow that down a bit. And this is where you can use something like a regular expression. So grep uses, if you recall a long time ago in the slides, something called the basic POSIX syntax. But grep with the TAC-E flag or egrep is going to use the extended syntax, which is almost identical to PCRE, which is a lot of the syntax that we've been talking about tonight. So I could do grep TAC-E and, excuse me. So then I want to find maybe in that URL a character that is going to start a SQL injection. So we'll say the single quote in this particular case. I think in the demo syntax I produced, because I was trying to think about like in access.log and it might still be URL encoded, it looked something like this. So it's a single quote or maybe a double quote. Actually, I have to escape that. Or the URL encoded form of that, which is %22 or 27. So I want to find that. And then I want to find anything that's not an ampersand, which would indicate a new URL argument, or a new line or carriage return, because I don't want to go into like the next line of data in the log. So I want to find 0 or more of those, and then I want to find select. So this is my regular expression now. Now, remember that conversation on efficiency? This is not super efficient. However, for the particular data that we're working with, it doesn't matter that much. Efficiency is important, especially like if you're trying to maintain a system that's going to be lifting a lot of weight. But for something like this, parsing logs, it matters a lot less. And then we'll pipe that to word count, number of lines. Now, this was a cyber defense exercise, so there were still a bunch of SQL injection attempts because someone probably just ran SQL map against it, or just did a bunch of like hand jamming to try and exploit something. So we at least cut it down by 2.5 times the amount of data that we might have to search through. But we can still do a bit better. Maybe like each one of these, like if it's trying it against different pages, they may be using the same payload multiple times. Yes.
Before you go further, could you change your word count to head so we can get like an example?
Yeah.
Like the first 10 lines that match, just so we get them
Yep.
in our head what actually did match.
Great point. Oh gosh, sorry.
Without working.
Yep. Yeah. So we're seeing in here. Let's scroll up to the top. So what it's looking like is it's got the URI, not including the domain, and then they've got some URI parameter, and then the injection in there. It's doing like union select, and it's trying to exfiltrate different types of data. So we'll see this on a couple different pages, obviously, and a couple different parameters. So if at this point we wanted to see like what does the payload itself tend to look like, then we can actually output matches with the TAC-O option for grep. And again, this can be TAC-E or it can be egrep. So either one, they basically do the same thing. And what I want to do is so it's outputting all matches. And then I also, on the other side of this, I want to go all the way to either a new variable. So I want to stop if I find an ampersand or a new line. Yeah. And I'm going to pipe that to sort, TAC-U for unique. Let's see what that word count looks like. I think it's significantly smaller. Yeah, we got like 10. So you can see a list of the different payloads that were thrown at this particular system. So yeah, that's a way that you can use grep to basically like fine tune what you're finding. This isn't a log. It could be a document. If you like are looking for like a specific pattern of a hash or a password and you don't know where it exists, but it looks like this, then you can do this on an entire file system. So and that is a case where efficiency might matter a lot more. But yeah, that's a way to employ regular expressions to like basically superpower grep. The next demo, I'm just going to skip down one instead of full screening it. It's going to be looking at Yara. This is how I tend to use Regex on a daily basis. So jumping back over.
And what is Yara?
So Yara is it's basically a tool for finding matches in a rule against a particular file. So that rule might contain different strings that it considers bad. It'll contain some logic to it. Like I want to find 5 of these particular strings, or I want to find this string, but I want it to be at this particular offset in the file. And it's basically a tool that's been developed by malware analysts for identifying, signaturing some of these malware based on like the contents of it. It is a static analysis tool. I think there's some systems that are able to use it dynamically, so like run Yara against like memory dumps. So like once an executable, for example, if it's packed, once it's been unpacked and it's sitting in memory, they can run Yara against it, something like that. But essentially, it's basically another tool that says, does this file have these things in it, and it applies some logic to it. But one of the things that it can do is it can use some regular expressions, which is pretty cool. So for our demo, I was looking a couple months ago at finding a way to detect some PowerShell, like malicious PowerShell tooling. And some of the things I was trying to find was invoke shellcode from the PowerSploit toolkit, or some pieces of malware that are like derivatives of that. So I use VirusTotal a lot in my research, and one of the things that I found were like there are Yara rules that exist to find some of these things. This one's written by a guy named Florian Roth. He's a huge malware analyst in the field. Like he is just crazy. He develops tons of these for just about everything out there. But one of the things I noticed with his is like he's looking. Oh, sorry. Again, yes. Boom. There we go. Let me do that. Okay. He's looking for like literal strings. So in Yara, if it's got a quote around it, like you're trying to find that literal string. I mean, there's some variation that you can do to it. Like I want to find this in ASCII, or I want to find it in ASCII or wide, which means there's like null bytes in between every single character. Like you can do a little bit with this, but for the most part, you're trying to find a discrete string. And one of the things that's problematic is this is signaturing the out-of-the-box form of this particular script. So I pulled down a couple of these. And hold on, let me try this. No, for some reason it's not getting my control while I'm in terminal mode. Okay. So there we go. So basically the syntax for using Yara, at least on Linux, is you call the binary, you give it a rule, and then you feed it either a file or a directory or whatever. So I grabbed these samples off of VirusTotal and ran it against the rule, and it finds 4 of them. Interestingly enough, it finds its own rule because the strings it's looking for are in the rule. But 2 of these it doesn't match, and we'll see what those look like here in a second. So the ones that it does not match are this one and this one. So we'll see what those look like in a second. And the reason why is, let me pull these out here. This is just, one of the generic ones. So this is like, again, the out-of-the-box version. Let me open this in Sublime. That might be a little easier to see. There we go. So again, this is the out-of-the-box version. Like everything's in plain text. Like it's very clear that this is like part of the Powersploit toolkit. So the things he's looking for are definitely going to be in here. One of the, sorry, wrong window. One of the ones that I was looking at was very similar, except it was a little bit obfuscated. Like they renamed some of the functions. They took out all of the comments. They put the shell code in this like from base64 string, like it was a base64 string instead of hex characters, and it also called slightly different, like this one called virtual protect and called window proc A instead of virtual alloc. Wait for single object. There's 2 other calls. But essentially, what I ended up doing is looking at this and like, okay, what is consistent between these? And regardless of like what the function names are and everything. And so what I ended up doing was, let me see, is this one in here? No, I put the original one in there. So what I ended up doing was finding some consistent stuff that I thought was not going to change. And what I landed on was this these 2 functions. This one, it's called GD and GA in this particular sample. Basically set up the get reflected delegate function and get process address function. It's basically a way to dynamically grab the code for a variety of other functions, like whichever ones you want for Windows. And consistently, each of the samples had these particular functions in them. And so I basically said, like, I want to find this regardless of whether these are like double quotes or single quotes, regardless of what, what it called, like whether it calls it type builder or whether it calls it something else, because this is just a variable name. Like they could call it like HHH and like it would still be valid as long as, they replace that variable name elsewhere in the code. So I said, like, I want to take out whatever's variable and like just find what's going to be consistent. And what I landed on was something like this. So I basically want to find get reflected delegate and get proc address. And so these are how you represent regular expressions in Yara rules. So you have to use the leading / and the trailing / to mark the beginning and end of it. This is another one of the reasons why / is one of those special characters that you do have to escape if it occurs somewhere inside of your expression. And then, of course, like these dots, like I have to escape them because they're, wildcards otherwise. Anyway, there's a little bit of variability. Like, for example, oh, sorry, yes.
Just a little context here. I know we're just searching strings, but this is PowerShell code.
This is PowerShell code.
So you can call the C libraries from PowerShell.
Yes.
Okay. That's interesting. How the heck does it force all the data?
So this particular, like this, structure right here, that's actually calling a something from the .NET framework. So more like, the C# .NET ecosystem, which is what PowerShell is built on top of. So that's why I saw that frequently in the malware samples that I was looking at. And so yeah, I had to find those things. I did see a couple samples where they were like dynamically compiling C# code, which is a different technique entirely. So this is a small subset of what I ended up creating because there's a lot of variety in how they do things. Like they can base64 encode this. They can, basically grab these things in different ways, because it's built on top of C#. They can call other functions. Like what I did not put into this particular one is I wanted to make sure it wasn't just this part of the technique that I was signaturing. Like I also wanted to see, like, is it calling the bad functions as well inside of the code? So there's a couple other things that I ended up doing with the final solution, but I just wanted to illustrate like how you can use regular expressions inside of PowerShell or inside of Yara. And it's a little hard to read, but this is one of the places in which, I use the power of regular expressions to match on more things, because this is a group, capture group. And because I saw some samples that said false here and some samples that said 0. So that's where I was able to do this. There were some that we used double or single quotes, so I wanted to find it regardless. Were there other areas where you guys get the basic ideas? Like I was able to give it a little bit of flexibility and I wasn't searching for just a raw string. So when I do run, hide that, there we go. When I do run this rule against the same directory, not only does it not find itself, but it does find all 6 of the samples, because since this was built on top of the invoke shellcode script from PowerSploit, it does contain, that same logic. And just for an idea of what does this do versus everything in the wild, I've got something called a retro hunt running in VT that I built. And you can see it is this same Yara rule that we just talked about. The cool thing about VT is it gives a little bit of that syntax highlighting. And right now it's found 1.7 thousand samples, and they should be relatively consistently malicious, because you'll see this particular technique not just in invoke shellcode, but in invoke mimikatz, and in it should be invoked reflective P injection. I've seen some Cobalt Strike beacon droppers that use the same kind of thing. So over here on the detections, you can see a lot of systems are finding this as malicious. And then even a couple of the ones that have pretty like low counts. If you actually open it up and look at it, VT has a hard time sometimes finding malicious PowerShell because it can be so severely obfuscated. So yeah, again, pretty consistently bad down the line. Ooh, beacon. It's interesting. Virus total. I say VT because it's just, shorthand, but it is like open source. Like anyone can upload something to it in order to see like, do I think this is malicious or not? But to do some of these things like this retro hunt functionality that I'm using, this is, behind a paywall, and I think kind of an expensive paywall, which my company pays for and not me. But it basically allows you to run YAR rules against basically like everything in their data set, or at least in the last 365 days. So, so this particular sample it found, again, it's hitting the same thing. Like they renamed some variables. They renamed the beacon itself is just a piece of code that comes back to, the bad guy server and says like, I'm here, I'm alive, give me something to do. And so then the bad guy can like send it code to execute. There's a couple like, basic commands like show me what's in this directory, read me this file, tell me what kind of system this is, that's already kind of like baked into like the basic version, or you can like insert more powerful functionality if, you've got that handy. So yeah, it's pretty cool. So it's also expensive. So yeah. All right. Our last demo, and again, this is pretty short, just showing you like, one more way that you might not expect that you have. Oh yes, that you might not expect that you can do it, but we'll see if this works just with, there we go. Okay. Oh, I can't expand this though. So the display filter at the top is just a way to like, narrow down exactly what packets. Oh, Wireshark. Wireshark is a way to look at a piece of network traffic. So, stuff goes between, point A and point B in packets. And this is just a really handy visual tool to be able to like look at each piece of data exactly as it flies over a network. This particular sample is showing someone attempting to exploit the Log4j vulnerability. If you guys remember that from a couple years ago, it was gigantic because basically everything used it. And the way it worked is like it sent a specific string into a server and got code execution that way, and like trivially. So if I was trying, like, let's say this was a lot bigger and, I was told like somewhere in here, the exploit occurred and go find it. And I don't know, much about it, but I've seen some examples of what that looks like. And for reference, what it kind of looks like is, oh, hold on. This should work actually, because nope, it doesn't. Maybe my control's broken. Shift control? No. Ooh. Aha. Okay. So it looked like something like this. And then address, code. So like something like this would, be in logs, and then once it's read by the Log4j server, like it executes it. So it looks something like this. But the other thing is this can be LDAP. The other protocol that was able to be exploited was something called RMI. Also, sometimes people like put characters in here. Like one of the obfuscation forms was this. Basically something like that. Like you could obfuscate this so that, if all I searched for was like, this particular string that I thought I was going to see, someone who was being particularly clever might get past you. So I was actually not able to get an obfuscated exploitation attempt. I can probably make one, but the time I gave myself, I didn't make it happen. But if I was to try and search for something like this, so somewhat trivially, I could say frame matches. Remember, regular expressions are trying to find matches of a particular piece of data. R means raw string. And I'm sorry, I can't zoom the actual bar any further. I'm going to escape the $, because remember, that's an anchor symbol. I'm going to escape the curly brace because I'm not quantifying anything. And then I'm just going to find J and DI. So that's all I'm doing right now. And it does end up finding it. It finds it in this GET request, which, gosh, they put it inside the user agent string. So no one wants to see the raw hex. There we go. So this is what this particular thing looked like. So it reached out to an address and calls back this. It's basically a malicious jar, if I recall. So, and then remember, we have that obfuscation strategy. So you might be able to find like, okay, I want to find 0 or more of these particular characters that I know are used to obfuscate this string right here. And I'll like put that same pattern in between the J and the N and the D and the I. And so I can still find what I'm looking for, but even if they try to obfuscate it, then this will still find a match. So it's another one of the ways that you might be able to use this if you're in Wireshark a lot and you're looking for a pattern and not simply a literal string. That is the end of my demos. Just as a preview for the future, some demos that I'm hoping to add before I do this talk again would be showing how this is used in snort rules in like a more advanced search in a SIM like Splunk or Elastic. How it's helpful if you're using Burp Suite to, define your scope or do some match and replaces, and then like what it would look like if you just wrote a Python script that employed these. So those are future demos that I'm hoping to add or replace current content with.
And you're currently planning to give this talk at the DEF CON 864 group, right?
Yes,
Okay.
DC 864 will. I don't have a time yet for when that will take place, but
We'll make sure it incorporates the additional.
right.
Which is a great group, by the way. DEF CON 864, you got to go to that. Thursday's your next meeting, right?
This Thursday.
These are some of those resources that I mentioned for learning more. Regular expression, tacexpressions.info has basically everything that you want to know, but it does go deep. Regex 1 is kind of like an interactive tutorial if you're someone who learns more hands-on. I know I am. Also Regex Learn, it's another one of those. And then here are a couple of cheat sheets that are useful to have on hand. Like I said, Regex 101 has something built into it, but if you're someone who you like to find the one that works for you and you want it handy offline, then those are some other ones that you could look at. And questions?
Just a tip on the Regex 101, you can host that locally pretty easily.
Yep.
A lot of times you're working with sensitive data, especially if it's logs.
Yeah, we have one in our intranet, so.
Yeah, just host it locally.
Yep. Great point. Any other questions or comments?
Questions online?
I don't have any, Jace.
Cool.
No one else has any questions? Seriously? About regular expressions?
You had
Second,
Yeah.
there we go. You had in one of the slides, there was a structure that had dot, star, question mark. What would that even be?
Yeah. So it's like purposefully like in there because it's a demonstration of like you don't want to do that because it is so ambiguous. And it's also a little redundant. So dot's the wild card. So it's basically could be anything. Star means 0 or more. And then the question mark is like it can be there or it could not be there. So it's like you're using multiple special characters to try and accomplish the same thing. Like if you really just want to find 0 or more of anything, dot star is the best way to go. So the question mark is redundant in that particular case. Yeah.
There's different languages that are different engines that'll behave different ways.
Yes.
I've seen that as a non-greedy.
As a non-greedy, yes. I'm trying to remember which one. I think it actually. Yeah, I'm not going to commit to one because I couldn't tell you. But yes, there is at least one engine that does do non-greedy matches, which means like if it finds so the way that might matter is in hop back over here. So if your regular expression is like A, B star, well, we'll say B plus, then a non-greedy match would be like, I found A, B, I'm good. I have succeeded in the regular expression. And if it's greedy, then it's going to match on everything. That mainly matters when like that's at the very end of the expression. But it kind of doesn't make a difference if you need to find a C afterwards. Then greedy and non-greedy are going to behave exactly the same way. So
Greedy, would it match like B plus B?
B plus B. Yeah, I mean, it would definitely match it because all that greedy means is it will go as far as it can, but it's still going to like find a valid match.
It's going to
If it's
backtrack
there.
one.
Right.
Once it,
Yeah.
And that's the problem with backtracking. Is that
Yeah.
There's some engines like the language Go doesn't allow that backtracking to
Mm.
avoid that security issue. Now, of course, that makes it less powerful.
Yeah.
But on the other hand, they don't have. Well, other languages like PHP and Ruby added not too long ago, they just had a timeout. And so,
yeah.
you know, if it still gives you the power, but they
Right.
can say no registration should last more than
Yep.
0.1 millisecond or whatever.
Right. So like in the B plus B, which is what we were talking about. There we go. Boom. Anyways, so yeah, the greedy one would go all the way here. And then, oh, I don't have a B. Let me backtrack one to see if there's a B. And, you know, then it would hit it. Whereas the non-greedy would probably stop. It would stop right here. Because it would find the minimum number of Bs that it needs and then the next B. So yeah, knowing that goes into like, you know, one of the common pitfalls, like know the nuance of whatever you're working with. So great question. Any others?
I was just gonna say you're brave for doing Regex live.
Yeah. I was a little nervous about it. Cool. Well, thank you guys for listening. I really appreciate it. Also, I don't know if you noticed, but I landed on exactly 42 slides. That is fortuitous.
Well, thank you very much, Duncan. We really appreciate you giving us a talk tonight. And I guess we'll say good night, everyone. Good night, Ben.
Good night, Jace.
We'll see y'all soon.
Bye.
Yeah, let's see. I was gonna say there were some. Oh, you wanted to talk about alt computing?
Yeah, just for a sec, if it's all right.
Yeah.
It's now good.
Yeah. That's a good
Yeah. So just real quick, tomorrow we're hosting an open house for this thing called alt computing, which is a meetup we're starting up. I think it was 1 or 2 Linux meetups ago. I don't know. I think 2 we did. We covered kind of one of the core things we're working on, which is this weird computer interface called Folk Computer, which is this, like, it's an operating system, it's a reactive database, it's a bunch of interesting things. So we're going to be working on that tomorrow. I'm going to be working on this weird propagator programming language that I'm working on. So yeah, if any of that sounds interesting, it's 6:30 till 8 at Synergy Mill, which is like 5 minutes away from here. Should be a fun time. So,
Do you want to expand on Thursday's DEF CON 864?
Yes, this Thursday, DEFCON 864 will be here. We start at 6:30. We generally go till 8, and then there's usually like an after-party dinner that happens after that. This week, I'd have to look on Meetup, but we're having someone local from, let's say it's like code enablement, so it's like knowledge and training, so they're kind of sharing what their program is and then what it's about. Didn't organize that one, unfortunately. I'm not read in what it is.
Anyone else want to talk about any other groups? Otherwise, thank y'all for coming. I appreciate it. This is like the biggest crowd we've had in a long time, and I'm humbled by seeing everyone, especially faces I hadn't seen in a while. It's really great to see everybody. Thanks. Hey, Ben.
Hey, Jace.
Arnold and Joey, good to see you. Y'all have a good night.
You too.